Welcome all to Module 3 of CS305 Microprocessors and Microcontrollers Part 1 presentation. In this session, we'll be dealing with the different types of interrupts in 8086, a special program called Interrupt Service Routine, and interrupt programming. Myself, Sridevi TR, Assistant Professor, Department of CSE, RSET. So basically, interrupt is something which distract or interrupt the normal execution of a central processing unit. So if you see this diagram, the central processing unit is executing the main program. It is following the normal flow of execution. But at this point, it is receiving an interrupt from one of the peripheral device called printer. Then the CPU, depending on the priority of that interrupt and also whether the type of interrupt is maskable or non-maskable, the CPU will be paying attention to that interrupt. It will do what all is required in order to satisfy that interrupt. Once it is finished with that, it will come back to the main program and it will resume the execution of it. So basically, the advantage of an interrupt when it is coming from a hardware peripheral devices like printer or keyboard, mouse, etc. is CPU does not have to waste its valuable processing time by polling such devices. It can be interrupted only when such device is coming with a data and interrupting the central processing unit, thereby saving lots of its valuable processing time, and it can use it for other functionalities. So whenever a processor is receiving a interrupt, it will jump to a special program called interrupt service routine to service that particular interrupt. So there are different types of interrupts in 8086, like hardware interrupts and software interrupts. Within hardware interrupts, we have maskable interrupt and non-maskable interrupt. We will be seeing each of these interrupts in the coming slides. So the first type of hardware interrupt is non-maskable interrupt. So as the name suggests, it is non-maskable. That is, the CPU cannot ignore the interrupts which is coming through the NMI pin of your 8086. And then it is having higher priority than the maskable interrupt request pin, that is INTR. And this non-maskable interrupt is of type 2 interrupt. So the for corresponding to or related to each of the interrupts in 8086, you will be having a type number, whether it is hardware interrupt or software interrupt. Either it will be explicitly given or it will be implicitly taken. So here for an NMI, it is the type number is 2. So when you are receiving a interrupt through this NMI pin, it will complete, the processor will be completing the current instruction that is in the progress, and after that it will soon pay attention to this NMI interrupt. That is, it will push the flag register value, the current values of your flag register onto the stack. Also, it will push the current CS and IP values on the stack. So whatever is required in order to resume its operation once it is completed, that interrupt is stored in the stack. Now the IP will be loaded from the contents of the word location 0008H. Why it is 0008H is, there is a data structure called interrupt vector table, which is starting from the beginning of your code segment. So each of the contents of this interrupt vector table are the IP address and the segment address of the various interrupts. Since the NMI is of type 2, how will you calculate which entry in the interrupt vector table gives you the address of that particular NMI interrupt, it will be given in 0, 2, 2 into 4, the type number into 4. When it is multiplied by 4, that will give you the IP address of that particular interrupt. And the next word location after this IP address will be your segment value, the code segment value. So that also will be loaded into a code segment register. So as you can see, your code segment is having the segment where your interrupt service routine is stored for type 2, and IP is having from which instruction you need to start. And so once it has identified the set of code needed for that particular interrupt, your interrupt flag and trap flag will be reset to 0. Next one is maskable interrupt. So as we discussed in the previous slide, it is having lesser priority than NMI. Again, it will complete once we get an interrupt from this INTR pin. It will first complete the current instruction, and it will be checking for the interrupt flag here. Since it is maskable interrupt, there is a provision for you to mask all the interrupts coming through the pin. If you are setting your interrupt flag equal to 0, that means any interrupts coming from INTR pin is disabled, or the processor will be simply ignoring that interrupts coming through that INTR pin, provided your interrupt flag is equal to 0. Else it will do the same what it has done for your previous NMI interrupts. It will be sending interrupt acknowledgement INTA to the hardware interface from where it has received it, and it will receive the interrupt type, say X. For NMI, by default it was of type 2, but here it can be of any type which will be received by the hardware interface when the processor is acknowledging that interrupt. So that X value will be taken, that will be multiplied by 4. When an interrupt type number is multiplied by 4, you will be getting the IP value for that particular interrupt routine or interrupt set of instructions, what you are supposed to do for that particular type number. And also the code segment value, the segment value of that instructions will also be loaded to the code segment from the next word location. So we have the code now for that interrupt. Once we get the address of that code, your interrupt flag and trap flag will be reset to 0. So far we have discussed about the hardware interrupts, the type of interrupts which is received through NMI and INTR pin of the pin 8086 pin IC integrated chip. Now let's talk about the software interrupts. The instructions are inserted at desired position to the program to create the interrupts. You have special instructions in order to bring interrupts in the program, or in order to interrupt the normal execution of the program. And the format of such software interrupts is INT followed by the interrupt type number. As we discussed, all the interrupts is having interrupt number along with it. So for hardware interrupts, it is implicit. Like for NMI, you have it will be coming as type 2, and for some other type of interrupts, which is actually implicitly given. But for a software interrupt, we have to implicitly give that interrupt type number. And in 8086, there are 256 interrupt types, and the execution of a software interrupts includes the following steps. The flag register value will be pushed to the stack, and then CS and IP also will be pushed to the stack. And like in our previous case, IP will be loaded from the content of the word location type number into 4. CS will be loaded the contents of the next word location, and IF and trap flag will be reset to 0. So to summarize, these are the differences between external interrupt and internal interrupt. In the external interrupt, the external device or signal will be interrupting the processor from outside, whereas internal interrupts, they are generated internally by the processor circuit, like a division by zero or some overflow interrupts, etc., or by execution of interrupt instructions like INT instruction. An example for external interrupt is a keyboard interrupt or a printer interrupt or any type of external device interfaces in interrupts. And external interrupts is only through hardware interrupts, whereas internal interrupts can be either hardware interrupt or software interrupt. There are two cases. And external interrupts, that interrupt type is implicit, whereas in the internal interrupt, the interrupt type can be explicit or it is implicit. Uh, when it can be explicit is when you give that interrupt number like INT followed by that interrupt number when you give a software interrupt. Then as we discussed in the beginning of your code segment, there is a data structure called interrupt vector table. So it is occupying a space address range from 00000H to 003FFH. That is the first 1024 bytes in the memory. And each entry in the interrupt vector table is 4 bytes long, and all these entries are either your interrupt IP address and the code segment address. So the first two represent the offset address and the last two the segment address of the ISR. And there are various divisions of this address space of 1024 bytes. The first 5 vectors are reserved by Intel to be used by the processor, and vector 5 to 255 are free to be used by the user. And every external and internal interrupt is assigned with a type that is either implicit, as in the case of NMI, trap, divide by, etc., or it should be explicitly specified in the instruction like INTN, as in the case of software interrupt. A special program called interrupt service routine will take the control of the CPU to a data structure called interrupt vector table, which is stored from the beginning of code segment, that is marked by 0000, then with an offset of 0000. So whenever the CPU is receiving an interrupt type number, that will be multiplied by 4, and that will give you the offset of the procedure which can handle that particular interrupt type. Soon after that word location, we will be getting the code segment address to in which segment that particular code is residing. So for example, if it is type 0, 0 will be multiplied by 4. You will be taken to this part, that is 0000 as the IP, the value address. So it will be taken the first two locations, that is a one word location for the IP address. So whatever is in 0000 and 0001 will be loaded to the IP register, followed by the next two address location, that is 0002 and 0003 will be taken to the code segment register. So that is type 0. Then you have type 1, which will be given by this CS and this IP combination. So what is the significance of this code segment and IP? You will be taken to that location where the code is residing to handle type 0 type of interrupt. This CS and IP combination will take you to that location where the code to handle type 1 interrupt is residing. So these are all pointers to the various interrupt service routine. The special program called interrupt service routine will be taking you to this interrupt vector table, which you have seen in the previous slide, which is starting From the beginning of code segment, we can address 000H offset, and it is like type 1 interrupt will be having the corresponding address for its routine at 0004H, type 2 at 008H, and so on. So the first four pointers are dedicated interrupt pointers. It has a defined purpose. Type 0 interrupts, they represent what to be done if a division by 0 interrupt comes. Type 1 is representing single type execution during the debugging of a program. Type 2 presents non-maskable or NMI interrupt. Type 3 represents breakpoint interrupts, which takes the operation into debugger. Then type 4 represents overflow interrupt. So if you summarize the 8086, we have 256 interrupt vectors, which is given in the beginning of your code segment. 00204 it's CPU exceptions including NMI. 8 to F they are hardware interrupts. 10 to 1F they are bias calls, like they can be considered as system calls, okay. And then 20 to 2F it's the DOS calls. They will be providing the DOS API in order to perform the various DOS functions, like to read something from the standard input, to read a character, to read a string, etc. from the standard input with echo or without echo. Then you can write something to the standard output. You can write the string to a printer. So all those things corresponding to all those DOS functions, you will be having sub functions within this DOS calls, like 20 to 2F. And 30 to FF is used by external drivers and user programs. So int21H is one of the frequently used interrupts for our application 8086 application program, since it provides you DOS API, as I told already. So if you give, so there are sub functions actually. So in 21H, you will be reaching that part of the DOS API. Then you multiply your 21 into 4. So you'll be reaching your IP address. The next word location will give you which code segment it is. Combining those two, you will be reaching that part of the DOS API. And in that you have sub functions. So for what, how will you mention that sub functions? You need to populate the AH register. If you populate your AH register with 01H and then invoke in 21H, you will be going to that sub function which helps you to read character from the standard input with echo. If you populate your AH register with 02H and then invoke the interrupt in 21H, you will go to that sub function in the DOS API, which will enable you to write character to the standard output. So like that you can see the various combinations of AH and in 21H. So this is how you address all the sub functions of your DOS API. So if you can analyze an interrupt type of programming, you will be using the normal execution flow. When you get a software interrupt, you will be writing it as int 09H. An example. So whenever an int instruction is coming, the type number will be taken. That will be multiplied by 4. It will go to that part of your interrupt vector table. It will fetch the IP from that memory location, word location. It will go to the next word location. It will also get the code segment. So combining those two, you will be reaching the interrupt service routine for that 09H, which could be a procedure. So the control will directly go from here to that part of the interrupt service routine, which we got by combining the IP and CS pointed by this interrupt type number in the interrupt vector table. So you reach there, you have started the procedure. When you get an end P, you understood that that particular interrupt service routine has finished. Then the control will go back to the next instruction after that interrupt call with type number 09H. So that is how an interrupt programming works. So if you see the interrupt response sequence, suppose you had your main program with main IP, main CS, and that process status word, which could be in the flags. So that status word CS value IP. It was there. So suddenly you got an interrupt of type N. Then what the system will do? All this status word, the code segment value and the IP value will be pushed to the stack. You can see this has pushed and then this and then this. It has been pushed, and since it is a stack type of thing, first PSW has been pushed, then it is growing downwards, then your main CS and then your main IP. Now once it is done, who will take the place of this? That will be calculated by type n into 4. So that 4n, it will go to that memory location. You will be getting the interrupt service routines IP value. The next word location will give you interrupt service routines code segment value. By combining these two, these will be taken the place of the CS register and the IP register. Okay, so once we get that CS and IP in code segment and IP register value registers respectively, you can start executing the interrupt service routine which is stored in that particular address. So that is the interrupt service sequence. So this can be nested interrupts also. You have your main program, and from there, suppose you encounter an interrupt type of type 0AH, it will go to that interrupt service routine for that interrupt type. It will execute that, and you may encounter another interrupt within that interrupt service routine, which here in this case it is of type 0BH. So the control will go to that interrupt service routine, and once it is finished, it will come back to your interrupt service routine of 0AH, and once this is finished, it will finally come back to the main program. This marks the end of part 1 presentation of module 3. Thank you all.